Swayam Prabha. Digital India. Educated India.
Hello students, welcome to the class. So today we will discuss something about the stereochemistry of the Diels-Alder reaction. So in the previous class, if you remember correctly, so we have discussed something about the 4 pi plus 2 pi cycloaddition reactions, which are named after the enormous research done by Professor Diels and also his student Alder, right? So the reactions are named after them, called as Diels-Alder reaction, right? So because of this discovery made in 1928 and enormous work done in this area, so they were awarded the Nobel Prize in 1950, right? So Diels-Alder reaction are highly stereoselective in nature and also regioselective in nature, right? That is what we have discussed preliminarily in the last class. Now in detail we will see how it is stereoselective or the stereochemistry of the Diels-Alder reaction. So we all know that Diels-Alder reaction is a thermal 4 pi supra plus 2 pi supra cycloaddition reaction. That means any dienophile coming in contact with the diene, the dienophile should approach the molecule in the cis manner only. So supra-supra addition will always help you to retain the stereochemistry of the dienophile, right? So therefore we got some idea that based on the stereochemistry of the reacting molecules, that is the diene as well as the dienophile, it is always possible to predict the stereochemistry of the cyclic adduct which is going to be formed, right, after the cycloaddition reaction. Now, so after observing n number of examples regarding this 4 pi supra plus 2 pi supra cycloaddition reactions, which is nothing but Diels-Alder reactions, Alder has concluded some rules. So those rules, those set of rules are framed as two types. One is the cis rule and the other is the Alder's endo rule. Now we will look into these rules one after the other. The first one we will be seeing now is the cis rule. So stereochemistry of the Diels-Alder reaction, and now we will be discussing about the cis rule proposed, developed by Alder and Steen, right? What is cis rule? Come with the diene separately and then we will discuss with the dienophile separately. See, any simple diene is nothing but a 1,3 butadiene. So where the sigma bond is generated is nothing but the C1 and C4 carbon atoms. If this is the C1, C2, C3 and C4 carbon atoms. Now as there are no substituents over here at the C1 and C4 carbon atoms, it is not required to think or worry about the stereochemistry of the cyclic adduct molecule, right? So when if you have a substituent, let us say there is a substituent R group and those R groups are aligned like this. So what does it say? At the first double bond it is trans in nature, that is E conformation, and at the second double bond also it is trans. So it is nothing but trans isomer, trans isomer of the diene, right, where the substituents are at 1,4 positions. The substituents are at 1,4 positions, because of which you are observing the stereochemistry here, and these groups are arranged such that they are trans at first double bond and also trans at the second double bond, right. If you ask such a kind of diene to react with any dienophile, let us say this one, benzene, it is an excellent dienophile, right. So what would be the reaction? So, this is a 4 pi supra plus 2 pi supra cycloaddition reaction, which is nothing but the Diels-Alder reaction. Now, always you will see the cyclic adduct molecule formed because of the reaction between this diene and the respective dienophile, and the stereochemistry, if you consider at the 1 and 4th carbon atom of the diene, what you will be observing here is both the groups, R groups, will be in cis relation to each other, cis related. So, both the R groups here are cis related. When this is happening, when the diene is showing the substituents in trans orientation, trans diene, stereochemistry diene, on reaction with any dienophile is going to generate a cyclic adduct molecule where the relationship between these groups is always cis, right. So, if you do the same reaction with another dienophile like this anhydride, maleic anhydride, so the same is what you will be seeing. So, cis relationship is again seen with the groups at 1 and 4th position of the dienophile. So, the groups are still in cis relationship. Okay. So, the first rule says that in a 1,4 substituted diene, 1,4 substituted diene, if the stereochemistry is trans comma trans at the first double bond as well as the second double bond respectively. So, then this kind of diene molecule on reaction with a dienophile is going to give you a cyclic adduct where the substituents at 1 and 4 position are always cis related to each other, right. So, that is the first rule. Now, second rule, if you slightly vary the stereochemistry of the diene, so this is trans diene and now we are changing it into trans cis diene or cis trans diene, whatever it may be. So, if the diene's stereochemistry is cis trans at 1,4 positions because of the 1,4 positions, still it reacts with the dienophile, which may be a benzene or which may be a maleic anhydride or which may be another dienophile, any reactive dienophile. Then the relationship between the substituents at 1 and 4 positions after converting itself into the cyclic adduct molecule is trans, That means you will be able to see the R groups in trans relationship. When it is happening? When the double bonds are exhibiting trans and cis stereochemistry. So, this is cis stereochemistry here and this is trans stereochemistry, that is if the diene is a cis trans isomer, on reaction with the dienophile, the cyclic adduct will show you the trans relationship between the substituents at 1 and 4th position of the diene, right. So, the same is observed here as well, trans relationship between the substituents. So, this is the second rule with respect to the diene. So, first rule says that if the diene is showing the trans relationship, then on reaction with a dienophile, so the cyclic adduct molecule will show the cis relationship between the substituents. If the diene is having trans cis relationship or cis trans relationship, so on reaction with any dienophile, the product would be showing the substituent in trans relationship only. So, if someone can ask you, right, what if both are cis to each other, both the groups are oriented cis to each other. So, this is cis diene. Cis dienes generally will not be available that easily for the cycloaddition reactions, that is the Diels-Alder reaction. Based on the bulkiness of these groups, the reaction may not be happening, If more the bulkiness of the groups, more will be the difficulty to participate in the Diels-Alder reaction, because the molecule itself tries to move to the transoid conformation. So, if the molecule is in transoid conformation, then it is not possible for that molecule to participate in the Diels-Alder reaction, right. So, that is there. So, generally the R groups may be either methyl group, or here may be a methyl group or a phenyl ring, right. So, this is the stereochemistry, that is with respect to the cis rule proposed by Alder and Stein. So, then what about the dienophile? If you have a diene, right, and if you have a dienophile, so the dienophile, if it is having some stereochemistry, COO C2H5, COO C2H5, let it be. So, this is a cis dienophile, where the bulky groups are on the same side, high priority groups are on the same side. This is a cis molecule. So, this dienophile will react with this diene, resulting in the formation of a cyclic adduct molecule, that is because of the 4-pi supra plus 2-pi supra cycloaddition reaction under thermal conditions, and the cyclic adduct which you will be seeing is always cis with respect to the dienophile's stereochemistry, right. So, this is always cis in nature. So, you can write like this. Yeah. If the dienophile is trans, still it undergoes 4-pi supra plus 2-pi supra cycloaddition reaction, and in the cyclic adduct what you will be able to see is that the trans stereochemistry of the dienophile is still retained. So, the trans stereochemistry is still retained in the dienophile. So, if the cis dienophile is used, the stereochemistry of the dienophile part in the cyclic adduct will be still cis in nature. If the trans dienophile is taken, the dienophile part of the cyclic adduct molecule will be always in the trans manner only. So, this is nothing but the cis rule proposed by or the empirical rule developed by Alder and Stein. Okay. So, now we will look into the Alder's endo rule. Alder's endo rule. So, what Alder has done after discovering this Diels-Alder reaction is, he started observing number of examples of Diels-Alder cycloaddition reactions. So, meanwhile, he observed that a particular stereochemistry of the diene will be giving you the particular compound with a defined stereochemistry, right. The cyclic adduct will be with a defined stereochemistry. That means, based on the stereochemistry of the reactant molecules, you can always predict the stereochemistry of the cyclic adduct molecule that is going to be formed, right. Now, when he observed the dienophiles coming with an electron withdrawing group, and specifically the electron withdrawing groups are the unsaturated functional groups, The electron withdrawing groups are unsaturated functional groups like carbonyl group, ester group, cyano group, something like that, right. When such kind of unsaturated groups are connected to the dienophile, which are in conjugation with the double bond, then to his surprise, so he observed that the final product is giving you two isomers. One is an endoisomer and the other is an exoisomer. So first of all, we need to know what is an endoisomer and what is an exoisomer first, right. For example, if you have a cyclic diene like cyclopentadiene, so this is a cyclic diene, and now if I have a dienophile, so when the Diels-Alder reaction is happening means the diene reacting with the dienophile, right. When Alder's endo rule is seen, means the dienophile, when it is connected to some other functional group which is an unsaturated functional group, this is an unsaturated functional group, right, carbonyl group, and this is in conjugation with the double bond of the dienophile, then he could always observe two different types of isomers. One is an endoisomer and the other is an exoisomer. When do you get an endoisomer? Means when the unsaturated functional group is underneath the diene, when it is approaching the diene such that the unsaturated functional group is coming below the diene, you will always see the endoisomer. If it is away from the diene, then you see the exoisomer. That means this will try to give you the endoisomer, whereas this kind of orientation will give you an exoisomer, right. So that means in the product, in the bridged bicyclic product which you are getting, see the functional group is underneath the diene part, and in some cases it is away from the diene part, right. So this kind of isomer is called as endoisomer and this type of isomer is called as exoisomer, right. So now Alder has a bunch of examples where he could see the endoisomer as well as the exoisomer only when the dienophile is having an unsaturated functional group connected to it, right. So then he formulated the empirical rule which is called as Alder's endo rule. And how we can define this Alder's endo rule means, according to the Alder's endo rule, when a cyclic diene, most of the cases cyclic diene only will show you this type of reaction, right. When the cyclic diene is participating in a cycloaddition reaction, that is the Diels-Alder reaction, with an unsaturated substituent attached dienophile, with a dienophile having an unsaturated substituent, then among the two isomers formed, that is endoisomer and exoisomer, always the endoisomer will be the major product. That means in crisp mode, how we can define this means, according to the Alder's endo rule, the diene, cyclic diene, if it is reacting with an dienophile having an unsaturated functional group, right. So you will be seeing two different types of isomers, that is endo and exoisomers. Among them, the endoisomer will be the major product. Why the endoisomer is major product? How can we justify this, that always endoisomer will be the major product? Conditions apply, right. So there are certain conditions, based on that conditions only you can predict that endoisomer is the major product. If you change those conditions, then the isomeric ratio, endo-exo-isomer ratio will also change, right. So how we can justify means, first of all, we have to see the reaction profile, energy profile for this reaction. Any cycloaddition reaction or any pericyclic reaction has to pass through the cyclic transition state, right. So now if you see the energy profile for this particular reaction. This is the reaction progress, x-axis, and this is energy, right. So, our reactant molecule is having certain amount of energy, and upon giving some activation energy, they are converted into products. They are converted into products, right. So, this is a kinetic product because the activation energy required is a little less, and also it is formed very fast in the reaction, right. So, this is an endo product. This is an endo product. Whereas, for the exo product, if you see the reaction profile, it is like this. So, this is an exo product and also called as thermodynamic product. So, you closely observe the reaction profile. The endo product is the kinetically controlled product and the exo product is a thermodynamic product. And when you compare the energy of this transition state, this is the energy of transition state for the endo product. So, this is transition state for endo product, and this is the transition state for exo product. Exo product. So, which one is higher? Of course, correct, right. So, the amount of energy, activation energy required to get the exo transition state is higher, and the amount of energy required to get the endo transition state is very minimal. What does it mean? The endo transition state are more stable and the exo transition states are less stable, right. So, endo transition states are more stable. So, transition state is more stable here, right. So, this is less stable because it is having higher energy, right. So, now when you conduct this reaction with a small amount of energy, immediately you can attain the endo transition state, which will further lead to the formation of the endoisomer, right. That means, endoisomer, the composition, the proportion or the ratio of the endoisomer is very high even at low temperatures. So, you need only minimal amount of energy, which is activation energy, and the stability of transition state for the endoisomer is also high. Therefore, at any given condition, you will get the endoisomer as the major product. But this is a kinetic product. This is a kinetic product. And one thing we need to always remember that the pericyclic reactions are mostly reversible in nature. Upon increasing the energy or leaving it for several days, several hours, or for an elongated time period, so what happens is it slowly goes back to the reactants. That means the reaction is reversible. What happens here? The kinetic product, which is a less stable endo product, upon increasing the energy of the reaction or upon prolonging the reaction time, what happens is the endoisomer will slowly go back to the reactant's place, and on gaining extra energy, it converts into the transition state of the exoisomer and gives you the more thermodynamically stable exo product. Thermodynamically stable exo product. Otherwise, you will get the endo product as the major product. So, this is the energy profile for the Alder's endo rule, that is the Diels-Alder reaction with a dinophile having an unsaturated system. Now, why is the energy of the transition state of an endoisomer is less? Why the transition state of an endoisomer is more stable? That is what we need to know now, right? So the transition state for the endoisomer is more stable, that is why it is quickly formed and therefore it is converting it into the endoisomer. The transition state of the exoisomer is less stable, that is why it is forming in a lesser amounts, lesser ratio, and then finally it is converted into thermodynamically more stable exo product, right? Why it is happening so? Now, if you consider the frontier molecular orbital approach, if you take help from the frontier molecular orbital approach to define this phenomenon, what does it say? Means the diene is having 4 molecular orbitals, that is psi1 2, psi2 2, psi3 0 and psi4 0. So the dienophile generally should have only 2 molecular orbitals, right, psi1 and psi2. But what is the speciality of this reaction means? Here the dienophile is in conjugation with the unsaturated functional group, right? So therefore it also contributes, and dienophile should also be taken as psi1 2, psi2 2, psi3 0 and psi4 0. And we all know that thoroughly Diels-Alder reaction is a thermally allowed reaction, right? So therefore you have to choose the homomolecular orbital from the diene under ground state conditions and also lumomolecular orbital from the dienophile in the ground state conditions only. Therefore the homo is psi2, this is homo, and the LUMO from the dienophile is psi3. So it is clear, right? So under the ground state conditions, we have chosen the homomolecular orbital from the diene, which is psi2 molecular orbital, and under the ground state conditions, we have chosen the LUMO molecular orbital from the dienophile, which is psi3 molecular orbital. So now, how do you see this psi2 and psi3? Psi2 means only one node will be there, plus, plus, minus, minus, right? So one node will be there. And for the dienophile also, psi3, this is psi3, this is psi2. Two nodes will be there, plus, minus, minus and plus. So you will see two nodes here. So these are the molecular orbitals. Now consider this thing, keep in mind all this data, and now we will see why the transition state of the endoisomer is more stable. When you are getting the endoisomer, when the additional functional group is underneath the diene molecule, right? So this is the diene, right? And so this is the dienophile. So this is the functional group. How you need to write? So this is the dienophile and this is the diene. Now, so how the diene molecular orbital is looking like? Plus, plus and minus, minus, right? And this one is plus, minus, minus and plus. So, this is C1, C2, C3 and 4 oxygen. So, this is 1, 2, 3, 4, 5, right. So, now this is C1, C2, C3, C4. This is 1, 2, 3 and oxygen, this is 4, fourth atom. Now, so always Diels-Alder reaction is a supra-supra reaction. What is happening here means this is the first orbital, second orbital, this is the first orbital and this is the fourth orbital. For the diene, the terminal carbon atoms will participate, and for the dienophile, first and second carbon atoms only will be participating in the formation of the sigma bond. That you need to keep in mind, do not get confused. This is the additional functional group attached to the dienophile, right. Now, so this will bind with this one. The C1 of the diene will bind with the C1 of the dienophile, and C4 will bind with the C2 of the dienophile. You see here, it is a supra-supra interaction. It is a supra-supra interaction. The lobe below is the positive lobe and the lobe above for the dienophile is the positive lobe. And here at the fourth carbon atom, the lobe below is the negative lobe and the lobe above is the negative lobe. So, supra-supra interaction. This partner is a supra partner and this is also a supra partner, right. Both are supra partners. And to our surprise, what is happening here means, besides the interaction of these primary orbitals that are required for the cycloaddition reaction, there are set of another orbitals both in the diene as well as in the dienophile, which are also interacting with each other. You can see here. So, this also interacting and this is also interacting here. So, therefore, besides the primary interaction of the molecular orbitals so as to form the cyclic adduct molecule, there are certain other interactions which are now treated as secondary orbital interactions, So, these secondary orbital interactions are stabilizing the cyclic transition state to a greater extent. So, that is why the energy of the cyclic transition state, particularly while it is giving in the endoisomer, is decreasing and the stability is increasing, right. So, the secondary orbital interactions, these are the primary orbital interactions, and this is secondary orbital interaction. So, on an endo approach, you can see clearly the secondary orbital interactions which are stabilizing the transition state for an endoisomer. So, that is why you will be often seeing the endoisomer as the major product. Whereas, if the molecule is approaching the diene in a different way, exoisomeric form, we will quickly see this. Right. So, this is plus, so plus, minus, minus and plus, right. You see now, this is 1 and this is 2, this is 3 and this is the heteroatom oxygen or any other group, right. So, this is 1, 2, 3 and 4. So, what is happening here? 1 and 1 and 2 and 2 are only interacting, that is only primary orbital interactions are seen. So, you are not able to see any of the secondary orbital interactions because these orbitals are away and these orbitals of the unsaturated functional group is also away from the diene system, right. So, therefore, there are no secondary orbital interactions which is making the transition state for the exoisomer very high energetic and less stable. So, that is the reason why you are observing the endoisomer as the major product, right. So, we will see few examples very quickly. So, let the cyclic diene molecule will be the common one, and if you make this molecule react with maleic anhydride double bond which is a dienophile, very good dienophile, right. So, you will be able to see two different isomers. One is endoisomer. Endo means the hydrogens are above. This is an endoisomer which is a major product. Alongside, you can also see the exoisomer which is a minor product, right. So, if this molecule is reacted with this dienophile, again you can see endoisomer plus exoisomer, right. So, if this is made to react with this dienophile, so again Cn plus exoisomer, right. So, if this is made to react with this dienophile, this is an endoisomer plus this is an exoisomer. So, whenever you see some of these dienophiles with an extra unsaturated system in conjugation with the double bond, there is an every possibility of the unsaturated system arranging itself underneath the diene, therefore giving you the endoisomer as the major product, right. So, when you go into the percentage of the products for some of the example, so take this reaction and this dienophile, right. So, always it is possible to see two different isomers. This is an endoisomer plus this is an exoisomer, right. So, as discussed already, the temperature of the reaction plays a crucial role in determining the ratio of the endo and exoisomers in degree centigrade. So, at minus 10 degree centigrade, the endoisomer is the major compound, which is about 85%, and the exoisomer is only 15%. If you increase the temperature to 110 degree centigrade, then the ratio is changing. So, this becomes 60% and this becomes 40%. If you further increase the temperature to 170 degrees, the ratio is simply reversing. So, endoisomer is 40% only and the XO isomer will be 60%. So, what does this refer to? Means at low temperatures with a minimal amount of energy itself, you are able to attain the kinetic product, that is the endo product. As the temperature is increasing, and we all know that these pericyclic reactions or the Diels-Alder reaction is reversible under high temperatures. So, the endo isomer, which is a kinetic product, is going back to the reactant molecules and reaching the highest energy of the transition state, and thereafter giving the thermodynamically controlled product, which is the XO product. So, therefore, upon increasing in the temperature, the percentage of XO product is increasing. The percentage of XO product is increasing. There is one such exception for this endo rule, that is the reaction of the dienophile with a diene like furan. So, furan is a aromatic compound. So, it being a dienophile and also an aromatic compound, it is little difficult for the furan molecule to easily participate in the Diels-Alder reaction, right, and thereafter giving you the endo product as the major product. So, it takes time. At room temperature, it reacts with the dienophile and then gives you the XO product as the major product on prolonged duration of the time at room temperature, because of the little less reactivity of the aromatic furan molecule as the diene, right. So, that is an exceptional case. So, at room temperature also, if you react it with maleic anhydride, which is one of the best dienophiles, at room temperature, about 64% of the reaction will take place, and on prolonged time for several days, if you leave the reaction for several days, so you will be seeing the XO product as the major product. Right. So, hope you have understood the stereochemistry of the Diels-Alder reaction. First is the cis rule and the second is the Alder's endo rule. Right. Cis rule says that, so if the diene is having the cis trans isomers at the cis trans positions at the diable bonds, so then on reaction with the dienophile, it will give you the trans adduct molecule. So, similarly dienophiles will carry, if they are cis before reaction, after reaction also they will maintain this cis stereochemistry, and if they are trans before the reaction and after reaction also in the cyclic adduct, they will maintain the trans stereochemistry. Alder's endo rule is mainly applicable for the dienophiles which are having an unsaturated functional group in conjugation with the double bond. So, majority of the cases when reacted with the cyclic diene like cyclopentadiene, so it will give you an endo isomer as the major product. But this reaction is highly stereoselective and also depends upon the temperature of the reaction condition, right. So, as the temperature increases, obviously you will see the XO isomer as the major product. Thank you. So, in the next class we will see about the regioselectivity of the Diels-Alder reaction.